All right, so the plan for today is to work our way through dividing polynomials and possibly get started on integer exponents and scientific notation. So that's the goal for today. And the quote of the day for today is actually by a friend of mine, Mark. He said this one time, and I thought it was a very succinct way to put this idea, so I wrote it down. So Mark is in finance. He deals with, obviously a lot of contracts and things like that. And he said, 10 times out of 10, I take a questionable contract with a solid person over an ironclad contract with a questionable person. And I thought that was a really good way to phrase it. I think of that a lot when I'm looking at hiring contractors. I think, okay, if I have one contractor where the paperwork is perfect, but the contractor themselves seems a little sketchy, and another one where maybe they're not so great at the paperwork, but they're the kind of person I would take just a handshake from. I'm probably going to go with the second one, right? If you get to the point in a business relationship where you have to take the person to court and rely on the contract, you've kind of already lost the battle. So now contracts are very useful to make sure that expectations are very clear and that both parties know exactly what the plan is. So there's certainly a utility to them, but I like this quote from Mark. So when you're hiring contractors, or at the end of the day, you're you're making a deal with that person. It's a person-to-person thing, and the piece of paper uh, ideally would be almost irrelevant, other than just making the expectations very clear. Okay. So sorry if my eyes are watering a little bit. My allergies are just going a little bit haywire with all the changes in temperatures. All of the different allergens seem to come out at this time of year. All right, so dividing polynomials. Let's do a quick recap of what we talked about last time. So last time we got a pretty good start on dividing polynomials. And we started off by recognizing that, well, if I can easily or feasibly rewrite my quotient of polynomials as sums of quotients of monomials, well, a monomial, as part of its definition, only has things multiplied together. And then if I have quotients of monomials, I kind of have multiplication and division mixed, and those two work pretty well together. Multiplication and division, I can do things like dividing out common factors, things like that. They mesh pretty nicely together. Okay, so if I have a polynomial divided by a monomial, if I have a polynomial in the numerator, something with some pluses or minuses in the numerator, but just a single term, just a one-term polynomial, a monomial in the denominator, then my strategy is to break this into multiple quotients of monomials. And we remember that, say, a plus b over c is a over c plus b over c. So we can break up fractions like that, whether a, b, and c are just numbers, or whether they have variables in them, the same operation applies. And now I have two subproblems. I want to simplify this quotient of monomials and also this one. And for the first one, I see that my 15 has a factor of 5. 15 is 3 times 5. The 5's divide out, leaving me with just 3 for the numerical part. And then I have x squared divided by x, or x squared over x to the first. That's x to the 2 minus 1 power, or just x to the first power, or just 3x from this first monomial. And then from the second, 10 divided by 5 is 2. And x divided by x, that's just the same thing over itself. Well, that's actually just 1. So just 3x plus 2 for this one. We can't simplify any further. We have no more fractions to try to divide out common terms. And these are not like terms, right? One of them has an x to the first power. The other has no powers of x. So this is our answer. This is as simple as it gets. We could look at a similar type of problem down here, 28y to the fourth plus 14y cubed over 7y squared. And again, we do the same thing. So I break this up into the sum of two fractions, each of which only has monomial over monomial. So the blue bit only has multiplication and division in it, and same with the green bit. It only has multiplication and division, so everything meshes very nicely within each of these little subproblems. 28 over 7 is 4. And y to the fourth over y squared, that's y to the 4 minus 2 power, or that's y squared. And then for the green one, 14 over 7 is 2. And y cubed over y squared is y to the power 3 minus 2, or y to the 1, which we'll just write as y. I've gotten to the end of my previous line. I take a look over this, this result that I have. I notice there are no common terms, or there are no like terms. There are no more common factors to divide out anywhere, nothing like that. No more simplification that can be done. This is my final answer. Okay, so polynomial over monomial, it essentially always works like this. We break up all of the terms into monomial over monomials, and then we simplify each monomial over monomial as much as we can, and then maybe look to combine any like terms at the end. Now, if we had polynomial over, say, a binomial, y to the power of 3. That's a 2. Sorry, I just wrote that kind of messy. Let's see, power of 2 there. Yep. If that was what you were referring to. If there's a, I don't think there's a different power of 3.
Yeah,
This one
that's
just,
it. I was
okay.
wondering if it's a two. I'm like, it looks like a three.
Yeah.
Okay.
Yeah, sorry, I just wrote it a little messy. Yeah, that's 4y squared. 4y to
Okay.
the second power. Yep. Now, if we're in a situation like this where we have a polynomial over, say, a binomial, something that's not a monomial, if we were to try a similar approach, like, say, doing x squared over x plus 2 and some other stuff, the problem is that our denominator has a plus in it. It has two terms. It's not as easy for me to try to find common factors or anything like that to divide out. I can't just do something like divide out this x with one of these x's and make this x over 2. That wouldn't be valid algebra. So I need to take a different approach in a situation like this. And the approach actually looks completely different. So it's actually quite a different approach. What I'm going to do here is I'm going to do polynomial long division. And once again, I'm going to just kind of remind us of what long division with numbers looks like. So let's say we have 417 divided by 3. So where would I start here? Well, I would say, okay, how many times does 3 go into 4? 3 goes into 4. It does successfully go into 4, and it goes in once. Then so I put the 1 above the 4. I do 1 times 3 is 3. I subtract that off. 4 minus 3 is 1. So that kind of finishes my first step. And then I start another step. I bring down the next number in line under the divided by sign. So I bring down the 1. And I ask, does 3 go into 11? Yes, it does. 3 times 3 is 9. 3 times 4 is 12. That's too much. So it goes in 3 times. 3 times 3 is 9. 11 minus 9 is 2. That finishes my second step. And then I bring down another number, bring down the 7. Does 3 go into 27? Yes, it does. 3 times 10 would be 30. That's a little bit too much. 3 times 9 is 27, right on the nose. 9 times 3 is 27. And we get a remainder of 0. So 417 divided by 3 is 139. And we could check that by seeing that 417 equals 139 times 3 and double checking. So we can do something similar over here. And remember the kind of trick, one last note from over here, the kind of trick is to think about a number like 417 as really being like 4 times 10 squared plus 1 times 10 to the first plus 7 times 10 to the 0. Or that's really just kind of 10 to the first is just 10 and 10 to the 0 is just 1. This actually is starting to look a little bit like a polynomial, right? If I have 1x squared plus 8x plus 12, or 4 times 10 squared plus 1 times 10 plus 7, that 10 seems to be doing something similar to what the x is doing over here. Okay, so let's look at polynomial long division. And as a side note, if you're really struggling with this topic, my recommendation would actually be to go back to maybe the beginning of the book or to Khan Academy or something like that and drill several of these long division problems with numbers. It's a little less abstract. You can see where everything is moving around to a little more clearly. And it's really exactly the same process. So if you're struggling with this, do 5 or 10 long division problems with numbers like this, and then come back to polynomials, and it should flow a little more smoothly. I have my numerator inside of the divided by sign, and then my denominator outside. Now I want to ask something like, how many times does x plus 2 go into like my leading term here, x squared? But it doesn't really make sense to ask how many times the whole x plus 2 goes into x squared. So ask something a little bit simpler. I'll just look at the leading term, the highest degree term, the term with the x to the highest power in both cases, and just ask how many times does x go into x squared? Or in other words, x times what equals x squared? Well, that's simply x, right? X times x equals x squared. Now I do x times x plus 2. So x times x is x squared. And then plus x times 2 is 2x. This would come in with a plus, but remember, we want to subtract this whole thing. So what I'm actually going to do is I'm just going to flip the sign of each term. I kind of mentioned this last time that this is a little thing that I like to do because if I have the negative out in the front, it's easy for me to make a mistake and kind of forget to distribute that negative. But if I flip the sign of each of the terms, then that distributive property is already done. I'm less likely to make an error with a negative. And now I just add down x squared minus x squared. I have 0 x squareds left. 8x minus 2x gives me 6x. Once I do this subtraction here, just like when I got to this point, I finished one full step of the long division process. And then what do? Well, then I bring down a term, say this plus 12, and I go and repeat the process. I ask how many times does x go into 6x, or in other words, x times what gives me 6x. Well, that's got to be 6. So I have a plus 6 up here. 6 times x gives me 6x. 6 times 2 gives me plus 12. So I have a positive 6x, a positive 12. And then because I want to subtract them off, I'm going to switch the signs. 6x minus 6x is 0. And also 12 minus 12 is 0. There's nothing left to bring down up here. I have no remainder. And that's my answer. Simply x plus 6. And if I wanted to check, is it true that x plus 6 times x plus 2 equals the numerator? If I multiply both sides by x plus 2, I should get x squared plus 8x plus 12. I do get x squared for my first. My outers and inners do add to plus 8x, so I get 6x plus 2x. And then my last plus 12. So everything looks good, and this is my answer. Okay, so I have 2 exercises for us to get a little practice on these. So we have one of the first type, and then one that I just did, the polynomial divided by binomial, to practice. So take maybe about, the long division does take a little bit of time to do, so take maybe about 6 minutes and work through these 2 problems. We'll come back in 6 minutes or so and discuss the answers. Okay, it's right at about 6 minutes. So let's look at these two. So the first one again, the plan is to break it into two terms, each of which is just monomial over monomial. So we have 30y to the seventh over 5y cubed plus 25y to the fifth over 5y cubed. And in the first term, 30 divided by 5 makes 6. And then y to the seventh over y cubed, y to the third, is y to the power 7 minus 3. And that's y to the fourth. So we have 6y to the fourth for our first term. And then our second term, 25 over 5 is 5. Y to the power 5 minus 3 is y squared. And nothing else can combine or simplify in any way, so this is our answer. 6y to the fourth plus 5y squared. The second problem was the, more lengthy one of the two. And again, this is a polynomial long division problem. So we set it up as x squared minus 4x plus 4 inside the divided by symbol, and then x minus 2 outside. And I want to ask something similar to like, how many times does the number in front go into like the first number in um my uh my numerator, my number that's inside the divided by sign. Right, I'm asking something similar to that. I'm asking x times what gives me x squared, and x times x gives me x squared. So I write x up top above my divided by sign, and I multiply through x times x minus 2 gives me x squared minus 2x, but I'm subtracting that. So I'm subtracting x squared minus 2x. And if I do the work of distributing this minus sign up front, that saves me from the potential of making an error later on with maybe forgetting to distribute it to the second term. So that's what I did here. Instead of writing minus parentheses x squared minus 2x, I just distributed that ahead of time and made it minus x squared plus 2x. And now I'm just going to add down x squared minus x squared. Well, the x squareds go away. That's why we essentially asked this question, x times what gives me x squared, setting it up so that whenever I multiply down, x times x gives me x squared, and those two exactly go away, and I reduce the order, I reduce the degree of the polynomial I have to deal with from that point forward by 1. My x squareds all go away, and now I just have x's and constants to deal with. So I'm just chipping away at the problem piece by piece. And then negative 4x plus 2x, well, that gives me negative 2x. So at this point, I have finished the first round of the algorithm. And then what do I do next? Then I bring down my next term, plus 4. I ask how many times does x go into negative 2x, or in other words, x times what gives me negative 2x. That's, of course, negative 2. So I put a minus 2 up top. Multiply through by negative 2. So I have negative 2. What's with my 2's today? Just can't write 2. Negative 2 times x minus 2. Well, that's negative 2x plus 4. And then I'm subtracting that. So this negative on this 2 came from this one up top here. And then in addition to that, I'm subtracting. So I have another minus out in front. But I notice I have minus 2x plus 4, subtract the exact same thing, minus 2x plus 4. That gives me 0. I have nothing left to bring down. I've taken care of all of the terms in the numerator. I have 0 remainder. This says that my answer should simply be x minus 2. And let me check this. If I have numerator over denominator equals answer, I should be able to multiply both sides by the denominator. It should be true that x minus 2 times x minus 2, this x minus 2 times that x minus 2, gives me the original numerator. And that does work out, so this is the correct answer. Okay, let's look at another example. Give me just 1 second here. Sorry about that. Hopefully my allergies will be a little bit better in a week or so after they adjust. I'm taking 2 allergy pills a day these days and still not completely working. Uh, okay, so let's look at this next example. We see the numerator is a little bit more complicated, but it looks pretty similar to the last one. So I think a similar strategy to the polynomial long division should work for this as well. So my numerator is 3x squared minus 10x plus 30. My denominator x minus 3. Okay, so I want to start by identifying my highest three terms. As a side note, everything has been kind of written nicely by default here. But if it wasn't for some reason, in each of my numerator and denominator, I would always write my terms from highest degree to lowest degree. So that way it's kind of analogous to like our number system where our number in the highest with the highest place value is furthest to the left, and then we get lower place values as we go further to the right. So I ask, how many times does x go into 3x squared, or in other words, x times what equals 3x squared? Well, I need a factor of x to make the x squared, and I need a factor of 3. So I think this has to be 3x. 3x times x minus 3. That gives me a 3x squared minus 9x. So I multiply through, and then I subtract this. And again, I'm going to just distribute that negative sign now. Make this a minus 3x squared plus 9x. And now I'll add down 3x squared minus 3x squared. The x squareds go away. That's exactly what I wanted. So from this point forward, I only have to deal with x terms and constant terms. Negative 10x plus 9x gives me negative 1x, or just negative x. Okay, so that finished, that completed one full round of the long division. I still do have some more material in the numerator I haven't dealt with. I have some stuff to bring down. The plus 30 can get brought down. And then I do another round. X goes into negative x how many times? Or in other words, x times what gives me negative x? Well, that's got to be just the constant -1. So I'll put a -1 up there. -1 times x minus 3 gives me -1 times x, plus -1 times -3 is plus 3. And then I want to subtract that. Or I see distributing the negative is going to give me a plus x minus 3. So it's going to give me a plus x minus 3 when I distribute that negative, and I add these together. Negative x plus x is 0 x's. Plus 30 minus 3, well, that gives me plus 27. I've completed another round of long division. Now I go up and I ask myself, okay, is there something else that I can bring down? Is there another term that can come down? No, there's nothing else there. Does x go into 27? Can I multiply x by anything to make 27? And by this, I mean like a monomial, like x to a positive power or a number or something like that. And the answer is no, right? I mean, I would have to have like a 1 over x or something like that. And that's not a polynomial. It doesn't have x to a positive power or just constant or whatever. So I really can't do anything else here. I've kind of come to a stopping point. I've come to a natural stopping point here. So it's a little bit like 3x squared minus 10x plus 30 over x minus 3. It kind of almost wants to be 3x minus 1. That's kind of the polynomial part that I pull off of it. But then there's a little left over, right? How do we handle that when we have numbers? Let's just take a really easy example, say 28 divided by 3. Well, 3 goes into 28 9 times. 9 threes are 27. So 28 over 3, we would say is 9. That's like the whole integer part that comes off of the fraction. And then we would say plus the remainder divided by the original denominator. So 9 plus 1/3. In other words, I'm thinking of 28 thirds as being like 27 thirds plus 1/3, or that's 9 plus 1/3, right? I have a bit that kind of divides nicely and gives me an integer as a result. And then I have a vestigial bit over here that just kind of sticks around. There's not much that I can do with that. I can't like make 9 1/3 somehow into an integer. It's fundamentally not an integer. Well, the same thing over here. This 3x squared plus 10x or minus 10x plus 30 over x minus 3, there's part of that that kind of divides out nicely, so to speak, and gives me like a something like an integer or really a polynomial piece where I've gotten rid of the fraction altogether. But then there's this extra vestigial bit. So I want to add on to this. What's left over? So plus 27 over x minus 3. So if I wanted to write out the answer mathematically, I would write it this way. Or sometimes I might convey this in a slightly different way, something like 3x minus 1 with a remainder of 27. You know, something along those lines might be another way to represent the solution. Now let's check. How do we check this? Well, just like before, if I have something divided by something equals something else, I should be able to multiply both sides by the denominator and end up with the original numerator. So let's check. What is x minus 3 times this stuff on the right? 3x minus 1 plus 27 over x minus 3. Let's forget about that, the fact that that 27 over x minus 3 looks kind of wonky. But let's just distribute. I can distribute this binomial into these 3 terms. Again, let's just forget about the last term looking kind of strange. But I have 3x times x minus 3 plus a negative 1 times x minus 3 plus 27 over x minus 3 times x minus 3. My first term I can distribute again. 3x times x gives me 3x squared. 3x times negative 3, negative 9x. Then I have minus x plus 3. And then for this last bit here, really I can think of the x minus 3 as like x minus 3 divided by 1. These fractions are multiplied together. I really have a common factor in the numerator and denominator that can divide out now. And I just have plus 27. Or that's 3x squared minus 10x plus 30, exactly our original numerator. So in this long division, x minus 3 doesn't kind of divide evenly or divide nicely into 3x squared minus 10x plus 30. We were left with a remainder part. But we got a polynomial part here that's kind of analogous to getting an integer or a whole number part over here. And then we were stuck with a remaining fractional part, the same way that we could be stuck with a fractional part over here. Okay, so let's do an exercise. Maybe take about um, maybe take about 5 minutes or so to work on this one. There are a lot of operations here, so go slowly. Don't try to rush it. Take your time. And, I'm giving you 5 minutes here or like 6 minutes for the previous, short problem and then a long division problem because I don't want you to see how fast you can get through it. I want you to take your time, really understand each step. There's a lot of negatives floating around. It's really easy to drop a negative, so take care with that as well. And so we'll take about 5 minutes. And as usual, I'll be maybe a minute or so behind you, kind of working through it. And we'll come back in 5 minutes and discuss the answer. Okay, it's just over 5 minutes, so let's take a look at this one. So here we have 6x squared minus 8x plus 3 over 2x plus 4. We have our leading terms 2x and 6x squared. So we ask 2x goes into 6x squared how many times, or 2x times what gives me 6x squared, and this is 3x. We write our 3x up top, and then I multiply through 3x times 2x plus 4, making sure to distribute that carefully, gives me 6x squared plus 12x. And then remember, I'm doing 6x squared plus 12x, subtracting that. So the like minus 1 distributed to 6x squared plus 12x gives me a minus 6x squared minus 12x. I add straight down the 6x squared minus 6x squared, the x squareds go away. So now from this point forward, I only have x's and constants to deal with, no x squareds. Negative 8x minus 12x is minus 20x. At this point, we've finished up one round of long division. Then I look back up top. I ask, is there anything else I can bring down? Yep, I can bring down a plus 3. So I bring down my plus 3, mark that off, and I do another round. Does 2x go into negative 20x? Or in other words, can I multiply 2x by something that looks like a polynomial? And yes, I can multiply by negative 10 to get negative 20x. So I put a minus 10 up top. Negative 10 times 2x plus 4, again, being careful to distribute to everything, is negative 20x minus 40. And remember, I'm taking negative 20x minus 40 and subtracting it. So I distribute that minus sign through, and that gives me addition of plus 20x plus 40. Negative 20x plus 20x, my x's go away now, so now I only have constants left. And then 3 plus 40 gives me 43. There's nothing else for me to bring down. And 2x does not go into 43. Right, 2x, I would have to multiply by like a 1 over x or something like that to get rid of that x. And that doesn't look like a polynomial. So at this point, my long division process is done, and my answer is 3x minus 10. That's kind of like the integer analog that came off. That's the full polynomial piece that divided out, plus a remainder piece, plus a fractional piece, plus this 43 over the original denominator, 2x plus 4. And if we check this, it should be true if I multiply both sides by 2x plus 4, I get the original numerator. So 2x plus 4 times 3x minus 10 plus 43 over 2x plus 4. Or I should have 3x times 2x plus 4 plus a negative 10 times 2x plus 4 plus 43 over 2x plus 4 times 2x plus 4. These are going to go away. 3x times 2x gives me 6x squared, and then plus 12x minus 20x minus 40, and then just plus 43 from the end here because those 2x minus 4s divided out. So just plus 43. Or that's 6x squared minus 12x plus, or sorry, plus 12x minus 20x is negative 8x. Minus 40 plus 43 is plus 3. And that is exactly the numerator we started out with. So we checked our work, everything looks good. As a little aside here, really what we're kind of saying here is, if I think of this 43, how can I make a 43 in this 6x squared minus 8x plus 3? Well, instead of having like plus 3, if I want a plus 43, I could do like, what, like minus 40 plus 40 plus 3. And then group these two together, right? So minus 40 plus 40 doesn't change anything. So minus 40 plus 43 still gives me a net plus 3 over 2x plus 4. So really what I'm saying is 6x squared minus 8x minus 40 over 2x plus 4. I have that fraction plus 43 over 2x plus 4. This first fraction divides nicely. It's the part that divides into 3x minus 10. So 2x plus 4 divides evenly, in a sense, into 6x squared minus 8x minus 40 and gives me a clean 3x minus 10, just a polynomial. But then there's this vestigial part, 43 over 2x plus 4. That's that fractional remainder. Similar to how I broke this into 27 over 3, that divides nicely into an integer, gives me 9. And then I just have my leftover fractional part. Okay, let's look at another example. So here we've got something that looks basically the same as what we had previously, but slightly different. My denominator is still just y minus 3, just a binomial, first degree binomial. My numerator, though, looks a little different. My numerator is actually a cubic, 2y cubed minus 4y minus 42. Let's try to do this the same way as we did before. And let's ask, how many times does y go into 2y cubed? I think that's going to be 2y squared, because 2y squared times y gives me 2y cubed. And when we subtracting, that's going to work out nicely. And then if I continue my multiplication, 2y squared times negative 3 is negative 6y squared. And I kind of see that I have run into a little bit of a problem, because now my kind of next column over has like some y's and some y squareds. It's not really like the end of the world. We probably could make this work out, but at the very least, it's going to be confusing. It's going to be hard to keep things aligned. So what caused the problem here? Well, what caused the problem is that my initial numerator is missing a y squared. It has 0 y squared and doesn't explicitly state the y squared term. This would be a little bit like if I had, 109 divided by 5 or something like that. I wouldn't want to write this as like 19 divided by 5. I mean, aside from the fact that this would just be objectively wrong, but like that 0 placeholder is actually important there. It's not just, turning one number into a completely different number, but it's serving a purpose of kind of keeping everything nicely aligned. Well, same thing over here. I do want to use the same strategy, of course. But I just want to make sure I put in a placeholder for any terms that I'm missing. So I see this is a cubic. My highest degree term is 3. So I have my 2y cubed. And then I work my way down. I want to make sure that I hit every term. I don't explicitly have a y squared term, but I'll just put in a plus 0 y squared. This is just a placeholder to give me a y squared column. I do have a y term, minus 4y, and I do have a constant term, minus 42. So I do want to make sure that I'm listing my terms from highest degree on down, and that I'm hitting every degree. And if I need a placeholder, I just give it a coefficient of 0, right? This coefficient of 0 in front of the y squared means that we could get rid of that and concatenate things back together if we wanted to, but we're going to keep it here for the time being as a placeholder. And then as before, I'll just kind of take my same process that I was doing before. Y goes into 2y cubed. How many times are y times what? Is 2y cubed. Well, that's got to be 2y squared. 2y squared times y is 2y cubed. 2y squared times negative 3 is minus 6y squared. And I want to subtract this. Or in other words, I want to change the sign of everything. Make that a minus 2y cubed plus 6y squared and add. 2y cubed minus 2y cubed, they go away. I have no cubes to deal with from here on out, just squares, y to the first, and constants. And then 0y squared plus 6y squared gives me 6y squared. I've now completed one round of my long division. Do I have anything else to bring down? Yes, I do. I'll bring down one more term. Bring down the next one, minus 4y. And then does y go into 6y squared? Y times what gives me 6y squared? That's got to be a plus 6y. And multiplying 6y times y gives me 6y squared. Multiplying 6y times negative 3 gives me negative 18y. Remember, I want to subtract this. I'll distribute that negative, making a minus 6y squared plus 18y, and add. My y squareds go away. 6y squared minus 6y squared, they go away. Then I have minus 4y plus 18y. That should be a plus 14y. I've got rid of my y squareds. I only have y's and constants left. I've kind of chipped away another little bit off of the problem. And I finished a second round of long division. Do I have anything else to bring down? Yeah, I actually do. I have a third round to go. Minus 42. And I can do the process one more time. Y times what gives me 14y? Well, that's got to be a plus 14. Multiply 14 through 14y. Minus 14 times 3. Well, hey, that's minus 42. That's nice. We are subtracting that off, and we see we get a thing minus exactly the same thing. That is 0 for the remainder. So this does divide evenly. It does divide nicely. My quotient should be just 2y squared plus 6y plus 14. And again, we can check. I won't go through all the details of checking just for time considerations, but it's not a bad exercise just to practice multiplying polynomials. But we want to check that y minus 3 times 2y squared plus 6y plus 14, check that that is actually equal to 2y cubed minus 4y minus 42. And as a little side note, when we do this multiplication, at one point, we're going to get a minus 3 times 2y squared, giving me a negative 6y squared. And at another point, I'm going to get a y times plus 6y, giving me a plus 6y squared. And those y squareds are going to go away. That's why we didn't see a y squared in this numerator. It just so happened that when we distribute this all out, we get a minus 6y squared or plus 6y squared. They go away. They make a 0y squared. We just don't write that. but we do keep it up here. We do put it back in as a placeholder just to keep things lined up properly, keep things running smoothly. Okay, so let's look at an exercise here. And I'll give you again about 5 minutes to work through this one. So here we have 27y cubed minus 125 divided by 3y minus 5. So take your time on this one. Remember to put in your placeholders, in this case, for both the y squared term as well as the y term. We're going to have 27y cubed plus 0y squared plus 0y minus 125. And despite this just being binomial over binomial, uh, we will end up doing several rounds of long division. Okay, so take the previous problem as a model, work through this one, take about 5 minutes or so. As usual, I'll follow behind you by about a minute or so, and then we'll discuss the answer. Okay, it's just over 5 minutes, so let's take a look at this problem. So again, main thing to realize here initially is that we're missing some of the terms in the numerator, so we'll put those in as placeholders. So we have 27y cubed plus 0y squared plus 0y minus 125 on the inside of the division symbol, and then 3y minus 5 on the outside. As typical, I ask how many times does 3y go into 27y cubed, or in other words, 3y times what gives me 27y cubed, and that's got to be 9y squared. So I write 9y squared up top, and then I multiply through 9y squared times 3y minus 5. I distribute that. That gives me 27y cubed minus 45y squared. And then remember, I'm subtracting that, so I switch the signs and make it negative 27y cubed plus 45y squared that I'm adding. The 27y cubed minus 27y cubed, my y cubes go away. I've now reduced my problem to only having to deal with squares and below. And then I get a plus 45y squared from the second column. At this point, I've completed one round of long division. I bring down my next term, happens to be a 0y, but that is what it is. Bring down my next term and go another round. 3y goes into 45y squared. Well, 3 times 15 is 45, and y times y is y squared, so that's 15y. I multiply 15y by 3y minus 5, and that gives me 45y squared minus 75y. And then again, I switch the signs and add. So I'm subtracting 45y squared minus 75y, or that's minus 45y squared plus 75y, making sure to distribute that minus. And now my y squareds go away. And my next column, 0y plus 75y, just gives me 75y. So I've gotten rid of the y squareds. I'm down to just the linear terms, the y terms, and the constant terms. So do I have anything more to bring down? Yep, I can bring down the minus 125. 3y goes into 75y. How many times? 3y times what gives me 75y? And that's just 25. 25 times 3 gives me 75, and the y is already there. So I put a plus 25 up top. I multiply through 25 times 3y minus 5, gives me 75y minus, and then 25 times 5 is 125. So I see I have a 75y minus 125 that I'm subtracting off, and I'm subtracting that from exactly the same thing, 75y minus 125. So their difference, of course, is 0. This does divide evenly. There's no remainder. It just ends up being 9y squared plus 15y plus 25. And then let's actually do the exercise to check this one. So to check this, I want to multiply this original denominator, 3y minus 5, by my answer, and that should give me the original numerator. Let's check. So I'll distribute 3y minus 5 into each of these three terms. And then each of these terms uses the distributive property again. 9 times 3 is 27, y cubed. 9 times 5 is 45, and minus 45, y squared. 15y times 3y is plus 45y squared. And then 15y times minus 5, 15 times 5 is 75. You can think of 15 as like 3 times 5, and then times another 5, that's like 3 times 25, so like 3/4, 75. 3/4, like 75 cents. So that's 75 and then y with a minus. And then plus 25 times 3y, that's plus 75y. And then minus 25 times 5, minus 125. And I notice that I get a lot of nice cancellation when I combine like terms. This minus 45y squared plus 45y squared, that goes away. The minus 75y plus 75y, that goes away. And I'm just left with 27y cubed minus 125. Exactly my original numerator. So I did check, and this is the right answer. Any questions on polynomial long division? So I think the biggest kind of hints or um, strategies, whatever it may be for this, are to realize that this process is really exactly the same process as we've done with just numbers. If you're not comfortable with this, if you're really struggling with this, I mean, this is the first couple ones we've done, but if you're going through the homework or you're practicing it and you still just can't quite get it, I would say go back to long division with numbers, drill 5, 10, 15 of those problems where it's a little less abstract. There's no letters floating around. There's less stuff like distributive properties and so on to worry about. Um, Go back and drill 5, 10, 15 problems with just numbers and get used to the process again, right? It's easy to kind of forget a little detail here or there with this process. And then come back to this and you might find that, oh, okay, this makes a lot more sense now, right? Because you've kind of firmed up some of the basics and now building on that to adapt it to variables and powers of variables and so on will be a little easier. So I think that's the first thing. And then the second thing is just taking your time, taking 50% more time, but getting a right answer is almost always a good trade-off. Take your time, be really careful with all of the negative signs, with all the distributive properties, all of that kind of stuff. So just make sure to get all these details correct. It's really easy to make a little goofy error here, and this ends up being minus 45 instead of plus 45, and it's going to throw everything else off from that point down. So it's fairly easy in a sense to get an answer that looks almost nothing like the right answer because of maybe one minor error early on in the problem that can kind of cascade through and just throw everything else off. So be extra careful with all of just the little details, especially the negative signs floating around. So those would be my main 2 pointers. Think of this just like long division of numbers, and be really careful with the details, especially minus signs. Okay, so moving on to 6.7. And I noted here for this section, assume all variables are non-zero so that we don't just have to say that every single example. We're going to talk about integer exponents and scientific notation. We've already talked a little bit about integer exponents. I cheated there a little bit and introduced that a little earlier, but we're going to discuss it a little more at length here. So let's look at simplifying this product, x cubed times x to the negative fifth power, in 2 ways, using the product rule and using properties of negative exponents. So we could use the product rule directly. What does it say? It says if I'm multiplying things that have the same base to different powers, I just add the powers, or 3 plus a negative 5 is 3 minus 5. This should give me x to the negative 2 power. Or another way I could do this is I could look at x to the negative fifth power. I know that x to the negative a is 1 over x to the a. I could look at this as x cubed divided by x to the fifth. I could rewrite my expression with positive exponents. And then I guess here I'm using my quotient rule. This would be x to the power 3 minus 5. Hey, that's exactly the same thing. Or if I chose to, I could write these answers with positive exponents, 1 over x squared, or 1 over x squared. So what if I want to simplify something a little more complicated like this? X squared times y to the negative third power, that monomial multiplied by another monomial. Let me actually zoom this in a little bit so these show up a little better. These negative exponents sometimes can look a little small. X squared times y to the negative third power, that monomial times another monomial, x to the negative fourth power times y cubed. Well, I know that this is just a bunch of multiplications, and multiplication is commutative and associative, so I can put all the x's first. X squared times x to the negative fourth power times y to the negative third power times y to the third power. Put the y's last. If I look at my x's being multiplied together, this is x to the 2 minus 4 power. And my y's are multiplied on as y to the negative 3 plus 3 power. Let's say 3. And 2 minus 4, of course, is negative 2. So this is x to the negative 2 power times y to the 0 power. We can write x to the negative 2 power as maybe 1 over x squared. And then y to the 0 power, that's just 1, right? Anything that's non-zero to the 0 power is 1. So all of this just turns out to be 1 over x squared. Right? What if I want to simplify something like this? X to the negative 2 power, that monomial, raised to the fourth power. I can use my power to a power rule. This is going to be x to the power negative 2 times 4, or that's x to the negative 8 power, or that's 1 over x to the 8th power. I don't know what my deal is with these exponents today, but there we go. 1 over x to the 8th, that's my answer here. I typically prefer to write my answers with positive exponents, even if that puts some x's or some variables in the denominator. I don't think it would be necessarily wrong to write this and say that it's simplified. But I tend to lean towards writing positive powers. And really, I guess the reason is that I'm just more used to, like, I kind of know what maybe the graph of 1 over x looks like. I know what I'm not allowed to plug into 1 over x. I can't plug in 0, things like that. So 1 over x to the 8th is kind of similar to 1 over x. But x to the minus 8, it looks a little bit more like, say, x squared or x cubed that, that has a very different looking graph or doesn't have domain restrictions on it, that I can plug in anything I want into, say, x squared. So I think that's probably the reason that I would kind of lean towards writing my simplest form with positive exponents, just because the pattern recognition is a little better there. But again, I think uh, it's a bit of a something that people argue about a little too much, whether or not like x to the minus 8th would be simplified. So again, as far as I'm concerned, I lean towards writing it with positive exponents, but for WebAssign, I would say if it says write your answer with positive exponents, then do it. Make sure that you do it that way. But for kind of, general purposes, whatever works best for you. And it's also a little context dependent. There are some contexts where if I'm doing a couple more operations, I might prefer to keep it as x to the negative 8th if that makes the next couple operations simpler for me to do. Okay, let's look at a few exercises. So that these just mirror the ones that we just did. So take maybe about I think this should take maybe 2 minutes. These should be pretty quick. Take maybe about 2 minutes, work through these exercises, and we'll come back and discuss the answers. Okay, it's actually around 3 minutes or so. Took me a little longer to write out all the details than I had expected, but so for the first one, we can do this two different ways. We can use the product rule. So y to the negative 7th times y to the 4th is y to the power negative 7 plus 4, or that's y to the negative 3 power, or 1 over y cubed. Or we can think of that y to the negative 7th as 1 over y to the 7th times y to the 4th, or that's y to the 4th over y to the 7th. And we can basically think of dividing out 4 powers of y from the top and from the bottom. And we end up with 1 over y cubed. For the second one, I don't know if you were paying close attention, but I made a silly sign error here, so it happens to the best of us, and you just have to be careful with your work. And when you make such an error, hopefully you recognize it and then you catch it. So I always do wonder, like, every once in a while I make an error and I'll catch it. I wonder, how often I make an error and don't catch it. I hope it's not too often, but um, so I rearrange my x's and y's to put the x's in front and the y's at the end. So I have x to the negative 1 times x to the negative 3. That's x to the power negative 1 plus a negative 3, which is what I meant to write, but I wrote negative 1 plus 3 originally, and then I went back and fixed it. And then my y's combining together gives me y to the power 4 plus a negative 2 or 4 minus 2. X to the power negative 1 minus 3 is x to the negative 4 power. And then y to the 4 minus 2 is y to the second power. Or this gives me y squared over x to the fourth. And then for my last problem, x to the negative 3 all to the negative 2 power times x to the fourth. We want to simplify this. I'm going to start working on my first factor, x to the negative 3 to the negative 2 power. That seems like the more complicated thing that I can simplify down a bit. Oh, why for the second one, not negative 1 plus 3? Yeah, for this one here, so we have x to the negative 1 times x to the negative 3. And our rule is x to the a times x to the b is x to the a plus b. Now, if this was a divided by sign instead, if I had x to the a divided by x to the b, then I would have x to the a minus b. Okay. So I hope that clarifies it. Yeah, so our third one, we want to start with this first bit here, x to the negative 3 to the power negative 2. And this is x to the a to the b equals x to the power a times b. So we multiply those powers, negative 3 times negative 2. And then that's going to give me x to the positive 6. You don't have to write the plus, but I wrote the plus just to be very explicit that this is a positive power now. X to the 6 times x to the fourth gives me x to the power 6 plus 4, or x to the 10th. Okay, let's look at something like this one. We have the product of two things. We have a product here. The first thing, the first factor is x squared over y cubed all to the negative 2 power. And the second factor, the second thing we're multiplying, is x cubed times y. So I think what I want to do is kind of similar to our last of the exercises here. I want to take the more complicated factor and work on it first. Try to simplify it down a little bit first. This one's actually maybe complicated enough that I'll maybe actually come off to the side over here and do some scratch work to work it out. Now I can use my quotient rule here and go this route. But I think what I might actually prefer to do here, there's a lot of negatives floating around when I do this. It's easy for me to make a mistake with a negative, as we just saw with the second exercise up there. I might actually prefer to get rid of this negative on the 2 first. So if I have like a over b to the negative c power, well, this is kind of like a over b to the negative 1 power raised to the c power, right? That's kind of just using our power to a power rule in the opposite direction, breaking the power apart into the product of two powers. But a over b to the negative 1, need a little more room here. A over b to the negative 1 is, well, that's 1 over a over b to the c power, or that is just b over a to the c power. So when I have a fraction to a negative power, I can flip the fraction and make the power positive. I think I actually want to go this route here. I think it's going to make it simpler. If you wanted to go the initial way, that's perfectly fine. It'll work. Just be super careful with your negatives. There will be a lot of negatives floating around. But here I can make this y cubed over x squared, flip my fraction, the positive 2 power. And now when I use my quotient property, I get y cubed squared over x squared squared. I don't have any negative exponents, just a little less likely for me to make a silly error with a negative sign. This is y to the 6th over x to the 4th. So that first factor all just turns out to be y to the 6th over x to the 4th times the second factor, x cubed y. Or maybe I'll choose to write this as x cubed over x to the 4th times y to the 6th times y. So being really comfortable with my fraction rules is super helpful here. Just the same fraction rules that apply to numbers also apply to variables. Things like, a times b over c is the same as ab over c is the same as a over c times b, things like that. Being really comfortable with all of these fraction properties is super, super helpful here. It means that I have a couple different ways to solve every one of these problems, and I can choose the tool that works best for the job at hand. So x cubed over x to the 4th, I can think of this x to the 4th like x cubed times x, or this is just 1 over x. Y to the 6th times y, that's really y to the 6th times y to the 1st, right? And this is going to be y to the power 6 plus 1, or y to the 7th power. And to clean that up a little bit, I'll just write that y to the 7th divided by x. And that's actually our final answer. 1 to the 7th over x. Let's take a look at this example. We saw one kind of similar to this in a previous section, where here we have kind of a negative sign that can be kind of inside of parentheses or outside of parentheses when things are getting squared. So we have to be a little extra careful here. Let's actually look at the last one first. Despite maybe the last one looking the most complicated, and the last one's actually, I think, conceptually the easiest. And the reason is I just have something to the negative 2 power. Parentheses, negative 3x, and parentheses, that whole thing is getting raised to the negative 2 power. That's just 1 over that thing squared. Or negative 3x all to the negative 2 power is just 1 over negative 3x all squared. Don't know what my deal is with exponents of 2 these days. There we go. And really this negative 3x, I can really think of negative 3x as being like negative 3 times x. I can think of it as the product of 2 factors. Oh, and I just realized I'm almost out of time. So this is 1 over negative 3 squared times x squared. This is 1 over negative 3 squared is 9, x squared. Give a little bit of thought to these two problems over the weekend. Do I get the same answer here? Probably not if I'm making a specific example out of this. What answers would I get here if I'm being very careful with exactly what is getting raised to the power? And we'll pick up here next time. Let me stop the recording.